seconds. Okay. I hope it started. Okay. I think we are online. So, okay, a warm welcome to all of you for this edition of the NSF Wednesday Colloquium. We have a fantastic world expert today with us who is going to talk about some of the very recent experiments that test general relativity and something as fascinating as observations made from binary stars. So, before I actually proceed with Professor Gopakumar introducing formally Professor Michael Kramer, I would like to state for those who are joining for the first time through YouTube channel that the Wednesday Colloquium has been a tradition, sort of age-old tradition of TIFR itself, where all the natural sciences faculty members get together under one, lecture theater and sort of listen to one of the renowned experts in any of the subfields of natural sciences, be it physics, chemistry, or biology. And it enables sort of discussion, not just with the expert, but also cross discussion across departments to understand sort of these nitty-gritties of the science that has, that came out through the talk. This has been a very successful forum, and I'm thankful that I'm sort of taking care of this for last couple of years, and there have been many coordinators like me who have been taking care of it almost 50 years now. So now, without further ado, I'd like to sort of ask Professor Gopakumar, who's a subject expert here, to formally introduce Professor Michael Kramer, who is our colloquium speaker today. Gopu.
Thank you, Jodishman and Kalo. It's a real honor and pleasure for me to introduce Professor Michael Kramer, Director of Max-Planck-Institut for Radioastronomy in Bonn. Michael, as is known to many of us, is one of the towering pulsar astronomers of our times. He has been, a big supporter of most of the pulsar activities in India. And well, he is definitely interested in using pulsars as a tool to probe many aspects of relativistic astrophysics, especially for testing general relativity and gravitational physics and cosmology. And he's also one of the experts on, pulsar astrophysics emission mechanisms, pulsars as a tool for, galactic probes and things like that. And these days, of course, he's very much involved in the hunt for nanohertz gravitational waves. And he facilitated very close interaction between Indian pulsar timing array and the European pulsar timing array, and supporting many of our activities. And so Michael is a director, but he also many awards to his name. I will kind of list few of them. Is a winner of Herschel Medal for testing JR and other things from Royal Astronomical Society. And a few years ago, we actually saw Michael was part of the the big Event Horizon Telescope discovery. And so naturally was a recipient of 2020 Breakthrough Prize in Fundamental Physics. And and he's a big promoter of square kilometer array, and especially using SKA for testing general relativity, gravitational waves, especially in the nanohertz regime. So without much further ado, I will love to listen to his talk today, and we are all excited about the new findings in double pulsar. Michael, please.
Thank you, Gopu. Thank you very much for these very kind words. Thanks for the invitation. And yes, it would be nice to see all the friends I see online here in person. So hopefully we can do this at some point. Let me share my screen and then I'll get started. Yeah, I think you can see this. Let me to this fancy laser pointer thing, then will make things easier. Yeah, thank you very much again. Yeah, I'd like to talk to you about some recent results on testing gravity with pulsars, in particular the double pulsar. And but before I do that, I thought I'd give you a bit of a context of how gravity, it should move on, yeah, has come a long way over the last centuries. And you may perhaps start with the idea that Galileo dropped different objects from the Tower of Pisa. Whether he has really done this in the way depicted on this diagram is a matter of debate. Or you can think about Newton sitting in the garden and watching the apple and making think about the laws of gravity. But certainly since Cavendish doing his experiments with his equipment, we really started to explore gravity in a rather systematic way. We didn't quite understand gravity. Certainly Newton's description of the orbit of planets was not sufficient, and soon in the 19th century, astronomers noticed that Mercury's orbit was processing faster than it was predicted, and they came up with a solution, for instance, that there may be an additional planet called Vulcan between Mercury and the Sun, and it's and because it's outshined by the Sun, you can't really see it. But of course, now we know it wasn't Vulcan, it wasn't the home of Mr. Spock, but it was actually the curvature of space-time around the Sun that caused that additional precession of Mercury's orbit. And so it was really that was the first test of general relativity, and maybe the second test was more spectacular when astronomers from the Royal Society in England organized 2 expeditions to Western Africa and Eastern Brazil to watch the solar eclipse in 1919, to measure the apparent positions of stars behind the Sun, noting that indeed they were displaced from their original position, which is caused by the light bending of the star on the Sun in the Sun's gravitational field. And that was, of course, the experiment that made Einstein famous. There are indeed many experiments you can do to test gravity, and each of them has their own right, because we are testing a really large parameter space. And one way of describing that parameter space, which is only one projection of many you can do on this multi-dimensional parameter space, is one where you can plot gravitational potential of your system versus the space-time curvature that you encounter in that system. And each of these dots is a different experiment. And I'll just highlight a few of them here. Sort of in the top right corner, we have the experiments that are now enabled by gravitational wave detectors. We have the beautiful observations of stars around the galactic center that was awarded with the Nobel Prize 2 years ago. We have spacecrafts that propagate, so look at the propagation of light via radio signals in the solar systems. We have lunar laser ranging, and we have the mentioned images of black holes, and we have also binary pulsars. And so each of these experiments has the potential of falsify general relativity and point to flaws in that up to now very successful theory. Pulsars are kind of unique because in terms of space-time curvature, they really probe a regime in terms of light propagation that is inaccessible by any other means right now. And so I'll give you one particular example about such an experiment in the coming couple of minutes. When you do such a diagram, you really have to be careful, because what we are putting on one diagram is actually a test in many different regimes of testing gravity. In the solar system, we really only test the quasi-stationary weak field regime, but very often to very good precision. If you start to see strong field effects, you can go to quasi-stationary strong field regime that's explored by pulsars or the mentioned S stars around the galactic center. But pulsars also allow you to get a first glimpse on the radiative properties of your theory of gravity. And if you want to really study this dynamical strong field regime, you have to do gravitational wave astronomy, which is possible now with the earthbound detectors, but hopefully also soon with pulsar timing arrays. And I'll have 1 or 2 slides on that as also. On the larger scales, you do look at the cosmology and more cosmic microwave background. And each of these methods is capable of providing extremely useful results for our understanding of gravity. In terms of radioastronomy, everything that I marked now in yellow is actually using radio technology, whether it's the signal propagation of the spacecraft, whether it's the Event Horizon Telescope, whether it's the CMB or pulsars, all of them use radioastronomy techniques. And this is really one of the things that I like about radioastronomy, because it is so versatile. The idea is really that we observe these very low energy photons, but most of them are actually created in high energy processes around compact objects. The good thing about the radio photons, though, is that they are easy to copy and easy to multiply, which allows us also to let them interfere with telescopes across the world or even beyond. And so we can synthesize huge telescopes. I mean, you have the GMRT, but you can even beyond with spacecraft go beyond the Earth's surface. And the good thing is about radio astronomy is that the emission that we receive propagates essentially undisturbed through the complete universe, really from the edge of the CMB to us right now. Also, unlike most other techniques across the electromagnetic spectrum, we can easily measure polarization, which gives us an insight into the magnetic fields in the source or on the way to us. And we get lots and lots and lots of photons, which means we can really resolve the universe on nanosecond timescales and really see the dynamic universe probably more than in most other areas of astronomy. And you use these radio telescopes. We have our own big radio telescope as well. This is about 40 kilometers away from where I sit right now, near Bonn. And then, of course, at the very end, I'll show some very, very few new results from the Nearcut telescope, which is going to be the core of the SKA. So this is all I really want to say about the introduction. I then want to go on and show you how we tested gravity with binary pulsars. I'll tell you a bit about the results that we obtained with a double pulsar. I can't help in pointing out some nice results of relativistic spin procession. I'll say a little bit about the universality of free fall, a basic principle of general relativity. And I'll say, as I said, a little bit about pulsar timing arrays before I summarize and conclude. Pulsars, I really don't have to explain this to you, and this should be an animation that moves. Pulsars are the rotating Newton stars. They emit the radio beam along the magnetic axis, which is inclined to the rotation axis. Whenever that beam points in your direction, you see a radio pulse. And as you know, these Newton stars are very extreme objects, probably the most extreme objects that we can actually study in the universe. The density in the center exceeds the nuclear density by at least an order of magnitude. They are highly magnetized of the order of the quantum critical field. And that implies electric field of the order of 10 to the 12 volts and electrical forces that exceed gravity by 10 or 12 orders of magnitude. And if you really want to understand that matter, that super dense matter, Newton star is the best way of doing this, because it's a high temperature superfluid superconductor. So it's material which you can never be able to create in an Earth laboratory. So if you want to study matter under very extreme conditions, that's the way to go. The experiment that we do is actually very simple. Conceptually, in practice, there's a lot of things to consider, but I'll sweep them under the carpet for the moment and just concentrate on the basic idea of the experiment. We start off usually with a pulsar, hopefully with a binary companion, and then we can see how they fall in the gravitational potential around each other, emitting maybe gravitational waves. They also emit radio waves that propagate through the interstellar medium, which is ionized and modifies the radiation in some degree. We then measure the arrival time of the pulsars on Earth, time tag them with our atomic clocks. We then analyze those data, compare the arrival times with what we call a timing model, from sort of taking the effects into account that we know of, and compare whether our arrival times follow this model. And if not, that means we have found some new effects or measured some different parameters. And that leads eventually to gravity tests, and as I will show you, also to constraints on a Newton star itself. That's the basic experiment. All we do really is to watch this laboratory that nature has given us from a safe distance, and just be the observer in that experiment. The first time that this was possible was in 1974, when Hulse and Taylor discovered the famous Hulse and Taylor pulsar. That was a system that they observed with their receiver telescope, which of course has now sadly collapsed. But at that time, we were able to measure a pulsar of a 59 millisecond period orbiting a compact companion that we now know as a Newton star in just less than 8 hours in a rather eccentric orbit, as you can also see from the variation of the pulse period of functioning orbital phase. And it was clear already at the beginning when they discovered that this system would be very new probe for testing gravity, predicting that it would actually be able to measure the decay of the orbit due to gravitational waves. And indeed that did. This is an observation much later. This is the latest paper on the Hulse-Taylor pulsar by Weisberg and Huang in 2016. And you know all this famous plot. The error bars are too small to be seen on this scale here. And the red curve is the prediction of general relativity for the emission of quadrupolar waves. And so this was really the first evidence that gravitational waves exist. But moreover, on a theoretical side, it also showed that energy is lost is exactly as predicted by GR's quadrupolar emission, that gravity propagates with the speed of light, and that gravity actually holds also for general relativity holds for strongly self-gravitating bodies, which wasn't clear at the time when this observation was made. And of course, it also showed that double Newton star mergers exist, and that was one of the major keystones why the LIGO observatories were finally built. The idea of how testing gravity uses nowadays a formalism that was really worked out in full detail by Damour and Jodrell, and later in a really nice paper by Damour and Taylor in 1992. And it uses a so-called parameterized post-Keplerian approach, where you basically amend your Keplerian description of the orbit by theory-independent post-Keplerian parameters. And they are, as I said, independent of the theory you assume, but every theory then gives, so you basically describe sort of the advance of periastron by an omega dot, you describe the decay of the orbit by time changing orbital period. You have a time dilation parameter and time parameters that describe signal propagation. And I'll come back to them later on in more detail. Every theory of gravity, or any reasonable theory of gravity, should then give you an expression that depends on a theory which contains only the two unknown masses of the pulsar and its companion and the Keplerian parameters. And you can see these are the equations here for general relativity, and they're structure-wise, they're all the same. They all contain a combination of the Keplerian parameters over the period and eccentricity and the two unknown masses. And here, so you have an equation where you basically have an equation of the companion mass as a function of the pulsar mass parameterized by your post-Keplerian parameter. If you plot them in a so-called mass-mass diagram, you basically get a line in such a plot, and each of this line is given by one of your parameters, and the shape of the line is given by a theory of gravity. So if your theory of gravity is a correct description of your experiment, then all these lines should intersect in the same combination of pairs for the pulsar, for the masses, the pulsar and the companion. In this case, schematically, this theory fulfills this. All equations have one single solution, and your theory of gravity describes the data correctly. If you see a plot like this, then obviously there is not a single intersection point, and the theory cannot consistently describe your experiment and therefore should be falsified. And so you need two post-Keplerian parameters to define an intersection point, and any additional line, any additional parameter that you get can then falsify your theory. And so you get n-2 independent tests of your theory if you have n post-Keplerian parameters. So that's the experiment. And if you look at what the Hals-Taylor pulsar does, here you have these three post-Keplerian parameters. There's one additionally measured, actually two, but much less precise. But the early ones were these three, the decay of the orbit, the precession of the orbit, and time dilation that we call the Einstein delay, and Einstein parameter. So they all intersect indeed in a single point. That's equivalent of showing this other red curve in the parabola plot on the previous slide. The Hals-Taylor pulsar was the best source of or best laboratory for testing gravity for a long, long time. But in 2003, we discovered actually a system that is even better. And we call it a double pulsar because it has actually two active and previously visible radio pulsars in one system. It is very compact, only 147 minutes in orbit. And the good thing is we see it from edge on, like in this version of the animation here. The deviation of this orbit from complete edge-on configuration is just 0.65 degrees. So it's really an amazing lucky coincidence that we see this orbit from really edge-on. We measure it very precisely, and that allows us to determine a number of relativistic effects. I will not go through all of them in my talk, but just tell you a little bit about the most recent additions to that list. If you want to read more, please visit that paper that we published at the end of last year. And you can also see the cast of co-authors, which are all very important in helping putting this data set together, which in total spans 16 years and comprises data of 6 telescopes plus the VLBA. So it has been a huge team effort, and it's not just me speaking about this, but lots of people involved. We have measured, for instance, the astrometry, the position of the system very precisely. We have a parallax measurement both from VLBI as well as from timing observations that give us a precise distance of 735 plus minus 60 parsec. And it also shows that the pulsar is actually more or less standing still in the galaxy. It has a very low transverse velocity. You can see that, and this is important for understanding some of the parameters, the double pulsar is actually rather close to the solar system. So there's very little relative acceleration between the double pulsar and the sun compared, for instance, with that of the Hals-Taylor pulsar, which is much further and deeper in the inner galaxy. In total, we have about 1 million times of arrival measurements. If you would spread them equally over the 16 years, that means we have an average cadence about 10 minutes. That's probably better than any other pulsar that exists. And that allows us also to measure the Keplerian, post-Keplerian parameters to extreme precision. For instance, we have measured the peristron advance, which rotates the orbit as a function of time. And by now it has rotated more than 300 degrees, not quite 360 yet, but getting there. We have measured that value, for instance, as is given here in this line, to precision, which is 35 times the contribution at the second post-Newtonian level. And that becomes important when we talk about measuring the moment of inertia in the system. The most striking effect, of course, perhaps that we see is the decay of the orbit. The orbit shrinks every day by 107,820 plus minus 7 picoseconds. That means that these pulsars approach each other every day at about a rate of 7 millimeters per day. And that means a merger in 85 million years. And that precision of this measurement will still improve with time. In fact, with Nearcut, we already have improved in that precision by a factor of 2 or 3. And by comparing the prediction of that measured decay with the prediction of general relativity, we'll find that they are in perfect agreement at a level of 1.3 times 10 to the minus 4 at a 95% confidence limit. And that's also expressed in the version of the parabola for the double pulsar. This is the same as in the Haas-Taylor pulsar. The blue data points are our measurements, and the red line is the prediction of general relativity. There's no fit to those curves. And at the bottom, you see the residuals of the measured values compared with the prediction of GR. So you see it's like pearls on the strings, and that leads to this unique constraint on the validation of GR. Actually, precision is so high that we have to take rather interesting effects into account. For instance, we have to take into account that the pulsar A is emitting electromagnetic radiation and therefore loses mass, E equal mc squared. And that means the orbital system loses mass. And that means, in fact, that's about 8.4 million tons a second. Sounds a lot, but actually compared to the mass of the neutron stars, it's a rather small fraction. But it's a third of our error budget. And so we have to take that mass loss into account for the very first time. What is also interesting is that we see higher order propagation effects in the light propagation around the curved spacetime of the pulsars. To first order, we see this Shapiro delay that everyone expects as the orbit is inclined to basically edge-on configuration. It means that the light, the photons of the background pulsar pass the foreground pulse on the way to Earth in just 10,600 kilometer distance. And again, if you compare the prediction of the effect delay that we see with the prediction of general relativity, then you see a perfect agreement as shown here on the left-hand side. Again, this is shown here in this diagram where the blue points are our error bars, our measurements with error bars, and the red curve is the prediction by general relativity. And it's so good you can't even see the red curve underneath it anymore. Actually, I'm not quite telling you the truth here. If I would zoom into this diagram, subtract the red line, we actually see a small deviation from that simple picture. Oops, that was too fast. So if I zoom into this green square on the next plot and subtract the red curve, without taking higher order effects into account, we see a systematic variation of the arrival times that is shown here. As we approach superior conjunction, the pulses of pulsar A start to become delayed progressively. And then at perfect superior conjunction, it switches sign, and suddenly the pulses come a little bit too early, of the order of about 3 microseconds or so. And then eventually it comes back to the expected arrival time sometime later. That is the result of 2 different effects. 1.5 pn Shapiro delay is one of it, which basically is a fancy description of saying that the speed of light is finite. So what happens is that when the photon of pulsar A is emitted by the time it reaches pulsar B has moved a little bit because it's moving with about 300 kilometers an hour in its orbit. And that means that leads to a shift in the Shapiro delay curve if you don't take that effect into account. However, that is not enough. That is just retardation. What we also have to take into account is light bending. What happens is that the space-time around pulsar B is curved. And since we are talking here about a rotating neutron star, we have an aberration effect. And so the light of pulsar A has to be shot before superior conjunction at a slightly later rotational phase in order to compensate for that light bending in space-time of pulsar B. That's why the pulse arrives a little late in terms of rotational phase before superior conjunction. After superior conjunction, the pulsar has to compensate the bending in the opposite direction. Hence, it has to emit the pulsar for the photons slightly earlier in rotational phase, as shown here in this diagram. And that's why the pulse seems to arrive a couple of microseconds early. And so this light bending actually contributes to 600 kilometers to this 10,600 kilometer distance I had on the previous slide. So this is the contribution just from the light bending in the space-time. And you can try to compare this with the expectation of GR. We can't really separate these effects of retardation and signal propagation and bending separately. But if you try to do that, you find that the is also consistent with the predictions. And this is shown here by the red curve that is shown in this diagram. But please read the paper with all the caveats of what I've just said. We also see that the orbit is actually not elliptical, but it's deformed. See this as as an Easter egg or whatever. This is highly exaggerated, but it's the result of a two-body motion in GR. So it's not the pure elliptical orbit, but it's actually sort of the X-shaped orbit in blue, highly exaggerated by about 6 or 7 orders of magnitude. But we measure the effect in a way that there's a correlation between the parameter which describes this deformation. We call it delta theta, as introduced by Moore and Jodrell in the 80s. And there's a correlation with the Einstein parameter gamma. And if you wouldn't take that value, that deformation into account, we would sit here on this 0 axis, and you can see that our best fit value would deviate by about 2 sigma or so from the prediction of GR, which is where the cross is. So we have to take this into account for the first time when we actually do our test of general relativity. And if you do that, then gamma is indeed in perfect agreement with the prediction of general relativity. And we have summarized this in this table here, and that you also find in the paper, where you have the relativistic effect that we measure compared to the observed and expected value on the right-hand side, and you see the agreement is perfect. In total, we have 7 post-Keplerian parameters plus a theory-independent mass ratio, and all of them then therefore produce lines in this diagram. This is the mass diagram for the double pulsar. These lines are actually 68% error strips of the measurement. So they are not lines, they're actually strips, as you can see here for the relativistic procession parameter omega. Geodetic, I'll come back to that in a second. But you can also see immediately that all of these lines intersect in a single point. And if you zoom into this, so very much zoomed in, and I'm not sure all the parameters, you can see now that omega is by far most precise measured value. This is just a thin line here. Then there's the Shapiro delay, then there's the orbital period decay, and the gamma parameter. What is also shown here are actually 2 lines of the periastron advance omega dot. The dashed line is the location of the omega dot, the periastron advance line, if you don't take frame dragging into account. But obviously there is frame dragging, at least as predicted by general relativity, and that it has a contribution to the observed value of omega dot. So if you don't take that into account, you would misinterpret where your intersection point is. Of course, at the moment, you still have the width of the period decay, and it's difficult to tell where it should be. But by shrinking down the error bar on PV dot, and this will be a function of time, we can then locate where the true intersection point is. And by measuring the distance of the intersection point to the line without frame dragging, we can measure the moment of inertia of the neutron star. And that is basically shown in this diagram here, which summarizes that the observed value of omega dot is the sort of value at first and second positron level without frame dragging, plus an explicit frame dragging lens steering contribution. And that lens steering contribution is proportional linearly to the moment of inertia. So if you're able to have that separation that I just tried to describe, you can measure what the moment of inertia and hence what the radius of the neutron star is, because the masses we have measured to very high precision. This is given from the intersection point of the mass diagram. Obviously, that depends on the equations of state. And And so we actually, these measurements here are marginalized over all reasonable equation of states. So we have taken that into account. And if you then try to get a constraint on the moment of inertia, at the moment, obviously we don't have the intersection point precise enough, but we can at least give an upper limit on the moment of inertia as shown in this diagram here. Obviously, it's not competitive with the values that have been observed with gravitational wave detectors or recently by NICER, but we are in the same ballpark. And the upper limit on the radius of the Newton star is 22 kilometers at 90% confidence. And even if it's not competitive with the other limits right now, with the other measurements right now, it's the very first time we have just determined the radius of the Newton star, an upper limit to it, just based on pulsar timing. And I think that's a nice thing to consider. With continuous observations, we will improve on this result, and we can either obtain our own measurement of the moment of inertia, and we have described it in this paper by our PhD student Hua Chen-Hu in 2020, or by taking the moment of inertia of other experiments as a given, we can turn this into a test of frame dragging in the near future. So either way, it's going to be nice. Since we talked about precession effects, let me also say a little bit about relativistic spin precession and actually moving away from the double pulsar in a minute. Geodetic precession, relativistic spin precession, to be more general, had been predicted for the Hals-Taylor pulsars immediately after the discovery of the system. There was a paper by Damour and Ruffini, which came even out before the first publication about that Hals-Taylor pulsar. And they already pointed out that geodetic precession will make the pulsar spin vector precess around the orbital momentum vector just because of the curvature of space-time. And that means that our line of sight would cut the emission cone under a slightly different geometry. And in this particular case, it would mean that here the pulse width would be wider than the pulse width at a different epoch. And this is exactly what we saw for the first time in the Hals-Taylor pulsar a few years later. This is a measurement with the Effelsberg telescope. And that was the first qualitative test that this actually was happening. There was a first initial quantitative result by Ingrid Stairs and collaborators on the second relativistic binary, but the first real test of this was really given by the double pulsar, where we used the effect that the pulsar is eclipsing actually for 30 seconds by the foreground slow pulsar as shown here. The magnetosphere is shown here as a donut, and the magnetosphere blocks the light of the background pulsar. So it's visible, it's blocked, visible, blocked, visible, blocked, and so on. And that leads to a pattern of that you see in the bottom of the visibility. And this pattern changes a function of time. Because at the moment here, you can see it's actually blocked for the full rotation of the pulsar B before it was half the rotation at the beginning of the eclipse. And so that pattern depends crucially and sensitively on the orientation of the spin axis of pulsar B. And as this processes, the pattern changes. And René Breton, his PhD thesis, could validate GR to 13% by modeling this eclipse. We actually have continued this experiment now with Nearcut. We can see here a beautiful eclipse pattern observed with Nearcut on the double pulsar. This is the light of B, and the stripes are the eclipses coming from this donut of the B magnetosphere rotating in front of it. This is much more precise than what we were able to do in the past by a factor of 3 or so. And then this is some preliminary result of the same experiment that René did, and now with Nearcut data. This is not the final result, but we expect ultimately that we can improve on the Breton result by about an order of magnitude or so. And this is work done by Markus Lower at Swinburne University, and Huan Chen in our institute is doing the other timing of the double pulsar with Nearcut. The hope is, of course, that with GMRT observations, we'll get a glimpse of the dispersion measure variations that we see in the data. And so the combination of Nearcut and GMRT will actually a very nice new contribution to this experiment. Another pulsar that is actually outshining the double pulsar in terms of spin precession experiment is a pulsar called 1906-0746. That's some result we published about 2.5 years ago. Here we have a pulsar which is also in a relativistic orbit. We only see one pulsar, but that pulsar is inclined or in a way with its magnetic axis that we see both poles of the pulsar, or used to do so anyway. So we see for one half of rotation, we see the north pole, and for the other half of the rotation, we see the south pole of that pulsar. And in one particular case, this is the beginning when this pulsar was discovered, the north pole was somewhat brighter than the south pole, but both of them were highly linearly polarized, showing this S-curve position angle swing that we understand from a so-called rotating vector model, which is basically when our line of sight cuts through that emission beam shown here from the top, and the linear polarization is along the plane of the magnetic fields. The projection of this direction on our line of sight gives you this S-like swing. This is pure spherical geometry. And that is at least the prediction of the model from 1969, which was never really be able to confirm, but probably was about right. This data set actually confirms it for the very first time, because what happens is that due to geodetic precession, the line of sight in the North Pole moves out of the beam towards the bottom here, and on the South Pole, it moved into the beam, and eventually, as I will show you in the next slide, has crossed the magnetic pole and goes further. So what happens is that when the line of sight is further away from the magnetic axis, this S-curve becomes shallower, and if you're closer to the magnetic axis, this S-curve becomes steeper. This is just some pure geometrical effect. And this is exactly what we see. If you just look at the South Pole, where we have crossed the pole eventually, you see that there was a shallow curve at the beginning, and the closer we came to the magnetic axis, became steeper and steeper. It became so steep we could actually not resolve it. But then the other consequences, once you cross the pole, the slope changes sign and it goes in the opposite direction. This is exactly what was predicted in 1969 and was now confirmed for the first time. And that gives you, again, the orientation of the spin axis of the pulsar to very high precision. You can follow the precession and so on. You can measure the rate of precession. And again, this value here is in excellent agreement with the expectation from general relativity. You learn much more about pulsars by itself. So this is another lecture. This data set is really rich. You learn much about the structure of pulsar beams and so on. But yeah, that would be another talk. Maybe I do this later. Let me then say a little bit about the universality of free fall, because that's really a cornerstone of general relativity, and GR may be, in fact, the only theory of gravity so far that fulfills this. The idea is simple. Coming back to the Pisa experiment, where Galileo seemed to have dropped some objects, in the weak equivalence principle, they just fall the same way, regardless on the mass. And that experiment is actually done with a microscope satellite in space to a precision of 10 to the minus 14, where we have two different test masses, different types but same mass, and therefore the same way. You can make that a weak equivalence principle to strong equivalence principle if you assume that they also fall independent of their composition, so of the self-compactness and self-energy. And so you can test this, for instance, in the solar system by asking the question whether the Earth and the Moon fall in the same way in the gravitational potential of the Sun. And that is done with the lunar laser arranging experiment, and tested to a level of 10 to the 2 times 10 to the minus 13. In terms of gravitational self-energy, that's a test at the 0.04% level. And of course, why do I talk about this? It's because you can do this experiment also with pulsars. And here you don't use the pulsar, the sort of the Earth-Moon system and the Sun, but you use the pulsar white dwarf system and a second white dwarfs orbiting around them, in the same way, which we call, and that's called the triple system that was discovered with the GBT by Ransom et al. In 2014. So there's the outer white dwarf produces an external gravitational field, and you can ask and observe the pulsar as it orbits a common center of mass with the white dwarf, whether there's any deviation to the orbit due to the fact that they may not fall in the same way due to their different compactness. And so if you do that experiment, and it was first done by Jodrell and collaborators using the triple system, and ask about the ratio of the self-energy, you see this test is actually better in terms of self-energy than what you can do with lunar laser ranging. We have repeated the experiment with an independent data set using the non-SAE telescope with very high cadence. We have done a different analysis, which is taken the systematics into account in a better way. We get a slightly better result, but essentially confirm the result of Jodrell et al. And this is so far the best test of the universality of free fall that exists so far in strong gravitational fields. There's much more you can actually do with pulsars, and that will be another lecture again. And I won't do this. I just put up some references here. If you want to look and read much more about these tests, these are good papers to start with, or you can see the recent reviews by listening Shao, Norbert Wex, or by Norbert and myself, and that should give you an overview about what's possible with binary pulsars. I'll say a few words about PTAs, and this was mentioned by Gopo at the beginning. Yes, you will have heard that by now all PTAs have announced that they see common red noise process, which means all of these pulsars that have been looked at show some feature that is could be the first sign of a gravitational wave background. The EPTA had seen the signal already in 2015, but we didn't publish it. But the fact that it has been increasing since gives us still a confidence that it's real. That confidence was lacking in 2015. That's the reason why we didn't publish it. But we also want to point out this is not a detection of gravitational waves yet. For this, we really need to see the correlation of the signal on the sky in a way it was described by the so-called headings and downs curves. And at the moment, we are working very busily, in particular also with the Indian PTA, on improving the data set, having more pulsars, and in particular, avoid some non-gravitational wave contributions to the noise. And the most important one here is the interstellar medium. And the good thing about the GMRT is that it has this unique wideband coverage, in particular also at low frequencies. And by measuring the dispersion, measure variations, and hence the interstellar weather coming from the interstellar medium, will help us to separate the intrinsic noise of the pulsars from the interstellar medium noise, and then hence hopefully can remove some of the uncertainties where this common red noise process is coming from. So stay tuned. This is very busy collaborations going on, and we meet our Indian colleagues very regularly, every other week or so, and that proves very fruitful, and I'm looking forward to see the combined data set. Eventually, indeed, with more sensitivity, we can indeed identify possible systematics, and hopefully can confirm that this is indeed a gravitational wave background signal that we're seeing. More sensitivity helps. For about 10 years now, we're doing regular monthly observations with the large European array of pulsars, LEAP, that we put together with an ERC grant that I once had. I don't know why I covered the Lovell telescope in Westerbork here. It's not very good. But it actually has the 5 large telescopes in Europe forming a 200-meter dish. Then, of course, there's the upgraded GMRT, which is really much more powerful than the GMRT in the past. So that's a really nice addition. Of course, we have FAST, which is twice the receiver collecting area. And on the southern hemisphere, we have Nearcut, which is really 7 times the collecting area of Parkes. So for those also that even the GMRT cannot see, this is really a major improvement in our sensitivity covering the southern hemisphere. And so we have this new kids on the block that really help us to make this a truly international collaboration, and hopefully together we can then converge to a detection of the gravitational wave background. Nearcut, just because it's such a beautiful instrument, let me give you 2 slides on that. My institute is heavily involved in Nearcut. We have built 64 S-band receivers. You can see them mounted here on a telescope. The commissioning is almost complete, and we will start science operations hopefully in the next couple of weeks, and the performance is truly awesome. Of course, as you know, searching for pulsars is one thing you want to do. It's rather hard with an interferometer, so you need a beamformer. And we have installed from our institute 2 HPC clusters at the telescopes and have built a beamformer which can synthesize about 10,000 beams on the sky. For data rates and sustainability problems, challenges, we reduced this to less than 1,000 beams. But that still produces 36 gigabytes a second or 3 petabytes a day. So we try to basically analyze the data and then wipe the disks and move on. And that's what we do rather successfully, also in collaboration with Ben Steppers at Manchester University, who is piggybacking and using part of our system for his Nearcut experiment, where he searches for transients and discovers FRB in basically real time. So that's really working, and it's very successful. We have already discovered more than 100 pulsars, about 60 millisecond pulsars we have discovered in the survey using Nearcut. The nice thing about, we're also doing galactic plane survey. This is led by the MPIFR, and it's unique in a sense. It's a fully conventional survey. It does pulsar, polarization imaging, and spectroscopy all at the same time. The bandwidth is very wide, 800 megahertz. And so that is a very nice contribution to the observations. And once the S-band commissioning is complete, we will also do the same thing at S-band for the inner galaxy, including the galactic center. And this is just one test observation of S-band. This is a rather truly clean band. It's high sensitivity. So we're really looking forward to use the S-band system on Nearcut, and stay tuned for some more results. And that really brings me to the end. I hope I could convince you that pulsars are really unique and precise sources for testing relativistic gravity. I really feel pity that Einstein didn't even see the discovery of pulsars. But so far, using them, we have confirmed relativity as good as we can. Our experiments are usually clean and precise. There's not much messy astrophysics in there because we have test masses and they have clocks attached to it. So it's the dream experiment. I haven't mentioned at all constraints and alternative theories of gravity, but consult the paper I was referring to. You will find that we have addressed 2 alternative classes of theories there. And this will go on. I mean, the precision will just improve with time. The more data we collect, that's true for the double pulse, that's true for the triple system, both of which really showed us that we have to step our game, particularly double pulsar. We have this many effects now, the higher order effects that we have to take into account, which means that we have to change the way we do pulsar timing. We found a lot of software issues that were taken for granted and now uncovered by the precision that we have. We really have transcended to the next level of precision, I would argue. And with new telescopes like Nearcut, LASPARS, like CMRT and SKA, eventually we will discover many more exciting systems. And so stay tuned. I think this is just the beginning of even more interesting discoveries. So there's much, much more to come. And let me finish with my favorite quote of Albert Einstein. There are so many things he said. The whole book's about his quotes. This is my favorite. The English translation of a quote of a letter that he wrote to Arnold Sommerfeld after he discovered that his theory can explain the Mercury perihelion advance is there comes the pedantic precision of astronomy to the rescue, which I have ridiculed silently so often in the past. And he refers to his amazement about the precision that they were able to measure the orbit of Mercury with. And so I'd like to think that he has also would have thought that would be a nice, impressive precision that we've done with pulsars. And I stop here. Thank you very much.
Thank you very much, Professor Kramer. Thank you very much. I would like to ask the audience, are there any questions for Professor Kramer? Yeah, Alok. Professor Alok Ray. Yeah.
Very nice talk, Michael.
Thank you.
I have several questions, and I don't know whether Gopu will allow me to ask so many. But let me just, ask one or two, at least one or two.
Okay.
You mentioned S-band observations towards the galactic center.
Mm-hmm.
Do you think you can detect pulsars near the galactic center, even in S-band, given the high degree of scattering measure?
The honest answer is we try everything to find a pulsar in the galactic center. We have tried a lot of things, frequencies already. We have searched with ALMA. We have searched with PICO at very high frequency. We have searched at low frequencies. We have searched a lot. The problem is indeed millisecond pulsars, for instance, will not be detectable even at S-band. But we also know that the scattering is rather patchy. I mean, if you look, for instance, at the galactic center magnetar, the scattering is much less than we had expected from the normal models that we have developed in the past. I will never give up hope. Finding pulsars in the galactic center was my PhD thesis, and look where we are. We still haven't found any. So I'll try everything. And the thing about Nearcut is that it's the first centimeter radio telescope that can beam us with very high sensitivity in a southern sky where we're not, in fact, affected by ground radiation and that sort of thing. So S-band is as good as high as we can get at the moment. With the SKA and band 6 receivers and so on, we can do even better. My dream experiment would be band 1 and ALMA, I have to say, that I personally think has the best chances of finding pulsars, in particular, since we would scratch millisecond pulsar population. So the short answer is, I think we just have to try. I think we need to. So we'll do it.
Okay, I will ask other questions later.
Yes, Alok. Yes, Alok. Please continue. Ask.
Ask now. Okay.
Yes. Yes.
Okay. So one of your slides tended to show that. I mean, you didn't comment about it at all, but one of your slides tended to show that you might be able to use pulsars as navigational tools for spacecrafts. Do you have any comments about that?
Did I actually refer to this? I can't remember. Leave on my slides. Anyway, I can, yes. To be honest, I keep my hands off this. Yes, it's possible, particularly not necessarily in a radio, but at X-rays. This seems to be a rather feasible experiment. And yes, I have written about this in the past. But to be very blunt, I think it has military applications, and I don't want to be involved in that, so I stay away from that.
Another one, maybe?
Can we ask Gopu for a second? Gopu? Yeah, then Alok.
Maybe Kalo can ask first, then I can ask.
Okay, Alok.
No, Kalo, I said.
Kalo has a question.
Right?
Kalo da?
No, you said Kalo has a question.
No, Alok.
Okay, no, I can ask then.
Yeah. Okay. Yes, Gopu.
Amazing talk, Michael. I have you mentioned that you were measuring next to leading order correction to the Shapiro delay. So so this goes back to the Kopeikin saga. So you are not talking about the velocity dependent. That will take a bit more time, right?
Higher order effects even, yes, that will take more time.
Right. Yeah, so I realized that that's not what you were kind of mentioning. I just got, this has the same problem when I went to I'm very happy to see that you are actually measuring the timing eccentricity, that correction, comes from that's amazing. I never expected that kind of, coming up from that. So in that connection, even you mentioned that the distance to the double pulsar, that is actually known up to the 10% accuracy. That's like the LIGO precision, 10%. Calibration is 10% problem there. So are there any way you can improve that? For example, having an Asian VLBI or something like that. Do you think that is actually required down the line? Because that is going to constrain you, even if you have much better timing telescopes.
Yes. We actually have to continue our observation with the VLBA and just with the existing array, and improving on some of the factors of the experiment. We have already, this is what Adam tells me, we already have an improvement by a factor of 2 or so, or 3 maybe even. So 2, I think, was the number he gave. So and predicting that into the future, I think we can achieve a factor of 10 in the future. But I certainly agree that having longer baselines to have higher resolution would clearly help.
So like the GMRT, POGs, FAST kind of thing with the bigger elements and including TIE, that's what we are kind of thinking about these days, as you know.
Yeah, so FAST can't see the double pulsar because it can't see fast out enough. But yeah, any other sensitive long baseline array would certainly help. So I totally agree. We have to try. We are somehow in a lucky position, though, in the sense that the contribution to the acceleration, the relative acceleration to the galaxy and the Shklovsky effect, they actually almost cancel each other in the double pulsar. It's in a very fortunate position. So we get away with the position distance that we have right now. But as the timing improves, you also need to improve on the distance measurement. But I believe with VLBI that's possible.
Thank you. I think I'm done. Alec, back to you.
I feel embarrassed because there are other questions. Maybe other questions should be asked for us, and then I'll come back.
No, Alok.
Okay.
Alok, it is fine. It is fine.
Balchandra has a question.
Balchandra, Professor Balchandra. Yeah.
Thanks, Michael. Fantastic talk as always. It was quite fascinating to hear such a wide range of things. My question is a little bit follow-up of Gopu's. So it's a small information as well as a question. The information is that we recently had good fringes with EVN, so in GMRT. So VLBI is certainly possible. So the question which I was that if the VLBI with European telescopes, and I think Sardinia was part of that, or one of the big telescopes was part of that. If that goes ahead, can we have a LEAP experiment? Do you think there is a scope for doing a combination of GMRT with the other LEAP telescopes to really have a very high sensitivity data? Yeah, that is possible. I think, more for other sources than for double pulsar, because Effelsberg can only see the double pulsar for 2 hours, so less than an orbit, unfortunately, because we're grazing the horizon because of the mountains around us. But other sources, and with the LEAP telescopes further south, like Nancy, like Sardinia, that is possible. We have done some preliminary, even fast LEAP observations. So we're working on a combination of these data sets. But that would be great if you could combine LEAP with the GMRT. That would be very, very nice. We should certainly explore this. Absolutely. Okay, thanks. There's a quick question on chat. Can tests be put on limits on modified theories of gravity, such as scalar tensor theories of gravity? Yes, read the paper. We've done exactly that. That was a quick one. Sorry.
There was another question which is about, can you test Horn-Deskey's theories with double pulsar or other pulsars? I'm not so sure. Yeah, this is from Shantanu. Shantanu, may you want to ask?
I have to expose my ignorance of not knowing what Horn-Deskey's theory is. Sorry, I'm an observer.
These are the ones motivated by cosmologists, I mean, to explain dark energy, Galilean theories, and so on and so forth.
Okay. In principle, yes, we can do this. The problem with most of the alternative theories of gravity is that they're not worked out in such a full way that we can confront them with binary pulsar experiments. Most notably, what we would need to know as a best example would be, what is the gravitation, what are the radiative properties of that theory of gravity? Then we can do easily tests. But as long as these theories are not worked out in a full consistent way, it's going to be hard. And in particular, if you have chameleon effects evolved, of course, you can always put a screening around your pulsar in some distance and so on and get away with it. But I feel it's a bit like epicycle theory, where you just put another tweak in your theory to get away from testing things. We have, as you will read in a paper, we have put a test on scalar tensor theories. We have also put a test on tensor scalar vector theory. So we modified relativistic modification of a Newtonian theory. And essentially we rule it out. This experiment is not particularly, the constraint is not particularly better than what LIGO has done in terms of precision, but it tests in particular the scalar charge of part of the theory. So I refer to the paper, but for most other alternative theories of gravity, it's a bit more difficult because they aren't worked out in a fully sufficient way. And that's why in this paper, we revert back to those particular classes of theories, because they're basically understood, and that's why we can then use for testing.
Okay. Yeah. Okay. Okay. So so Alok, you can ask your question now.
Thank you. You mentioned that you could, for the 0737 binary pulsar, you could determine the m dot, the mass loss from. Do you mean the pulsar, the pulsar A itself, or from the whole system?
From pulsar A, and we did not determine it via the gravity test. You measure it because you can see how the pulsar is slowing down. So you actually get it very easily from P dot, right? And that you can convert into a luminosity, and the luminosity you can convert into a mass. So we know this very, very precisely. We can measure it very precisely. And if you calculate what the mass loss it corresponds to, it's about a third of our error budget. So if we wouldn't take that into account, we would shift our experimental data in the wrong direction. The same thing, we take the 3.5 PN contribution into account when we calculate the PB dot contribution. So we didn't determine it from the gravity test, but we need to take it into account to have the most precise comparison between our experiments and the prediction. And yeah, you can just measure it because we see how the pulse is slowing down.
But I suppose this kind of nice thing would not be available to you if you were to have a companion which is not a relativistic pulsar. Let's say if you have a Black Widow pulsar, you wouldn't be able to do it, right?
You could still measure the mass loss by looking what the pulsar does, but it wouldn't be completely useless in your timing, because the timing is no, it's the first. The way I phrased it, I think, is correct. Is we needed to take it into account for the first time. In this system, we have the precision that forces us to consider it, and there are no other system right now where this is possible. But that's why I mean that, in a sense, that we have to send it to the next level of precision. This is possible because of our data set and our precision, but with telescopes like the SKA, this becomes more routine, and you have to take these effects into account for other pulsars probably as well. So we see this a bit as a blueprint of the experiment and the things you have to consider for the things to come from now. And just to specify, yes, it's the mass loss of pulsar A, but that means, of course, the whole system is losing that mass too.
Okay. Okay.
I think Yashwant.
Yeah, Professor Yashwant Gupta.
Yeah.
Yeah, sure. You can hear me? Hi, Michael.
Yes. Hi, Yashwant.
Enjoyed your talk as always. So you didn't dwell too much on the gravitational wave detection business, but I just want to push you a little bit on that and see, especially because we've been discussing some of this in the IPTA detection committee. So you claim about this correlated signal, and then you mentioned that you need to be able to see the Hellings and Downs curve, right? And I guess there is this issue of how many reliable pulsar pairs do you need to see the Hellings and Downs curve, without any ambiguity? And given the number of quality timing pulsars that we have, and somebody like you is best placed to see, and the rate at which that number is growing and their sky distribution, what's your own take on whether the current number of pulsars in the data set is really sufficient to reveal the Hellings and Downs curve?
We have about 40 pulsars, probably nanograph and EPTA each, maybe approaching 50. We'll have exclusive southern pulsar included in the array of similar amount, maybe somewhat less. So we're talking in total probably about a number approaching 100. I would have thought, without doing simulations, that should be sufficient if the coverage of baselines is sufficient.
But are all of these 100 good ones that they will give you good pairs, or?
Sure. Yes, if you do this dropout analysis and so on, you will find that much less are contributing to the results. I totally agree. So I think, that's why I also think we need to be cautious in what we claim. So I hope that the new data set, the increased data set is giving us detection. But I would certainly be not the person running around and claiming we have a firm detection soon. I think we have to convince people that this is real. There is no other data set to confirm this. This is all the pulsars we have, and extraordinary claims need extraordinary evidence. And so I think I speak here for my European colleagues, we are very much on the cautious side and would really like to test all possible alternative explanations of what we see.
Okay, thanks.
Thank you very much, Professor Yashwant Gupta. I would then actually, if there are no more questions, yeah, that's what it seems like. I would like to thank Michael very much.
One more?
Alec will never stop. So
Alec has still got his hand up.
He will never stop.
Go ahead.
Michael will be here till next 3 hours. So.
One more.
Okay.
Look, I will give you the floor. It's okay. You are one of our sort of most most sort of beloved members. You always attend every colloquium, so I will give you that one question. Yes, please, Alok.
Thank you. You mentioned that there have been 1906 pulsar.
Yeah.
And it seems, I may be ignorant about this question, but I'll still ask this. It seems to me that this would be a source, a target, which would be a very good precision test of Radhakrishnan polarization model.
Yes.
Have people utilize this properly, and what are the results?
The result is in the paper. Yep, it works beautifully, and we get the geometry out, which is in perfect agreement of GR. So this is the best test of the Radhakrishnan curve that you can imagine so far.
Okay, thanks.
It's just read the paper. Yep.
Thank you. Okay, with that, Michael, thank you very much for keeping the colloquium in time, as well as answering all the questions, enthusiastic questions from the audience here. Unfortunately, we can't host you, otherwise we would have actually hosted you for a lunch as well as a tea snacks that is usually arranged after the colloquium for the guest speakers. So unfortunately, all those are kind of remaining. When you come next time, we are going to treat you with that. Okay. So I want to thank all of you for coming and sticking by today. A slightly delayed colloquium start at 5:30. So thank you to all the Indian audience here for taking care and being there. I would like to also make an announcement that our next colloquium is also a special one. It's going to be given by Professor Deepak Dhar, who recently won the 2022 Boltzmann Medal. So he is going to give his sort of a colloquium talk which led to the medal that he won. He's the first Indian to win the prize. So absolutely join in through YouTube, Zoom, whichever medium. It's a big event in Homi Bhabha at TIFR. So it will be a physical colloquium by him. So with that, thank you again, and I would like to conclude. Just for everybody, could you please unmute yourself and also just give a big round of applause for Michael for making this time and giving us a wonderful session. Thank you.
Much appreciated. Take
Thank
care.
you.
Thank you very much. Bye.
Bye.
Bye-bye.
Bye.
Bye, Michael.